Hello, welcome to the part three of the lecture. In part one, we discussed about scatter plot and test of hypothesis, scatter plot, measures of association, and test of hypothesis regarding correlation. That was part one. In part two, we discussed model adequacy, comparison of models, and other inferential methods in regression analysis. In this part three, we will start with modeling bivariate relationships. In this case, that means we are going to consider one y variable, which is usually called the response variable or sometimes called the dependent variable. And we will consider another variable usually denoted by x. It is called explanatory variable or independent variable. Right. So suppose you have a situation, you think that your response is depending on mainly on one variable x. Then you want to find out what kind of relationship, and then you want to build a model to describe the relationship between y and x. Suppose that x is an explanatory variable, y is a response variable, and there is some kind of stochastic relationship, right, between x and y, right? Stochastic means random, right? So stochastic relationship is a relationship between two random variables in this case. For different experimental units, like maybe different experiments itself, or maybe you are taking observations from some, like main people or some instruments and so on, experimental unit on which you get a x value and a y value. Or in repeated experiment with a fixed value x of capital X, it is possible for y to take different values. Right? Even though you observe several experimental units with the same x values, their y values can be different. Or even if you do some experiment, say for example, to measure the strength of compressive strength of concrete, where your x is some variable, if you're even if you are keeping that value of the x variable fixed, if you are uh, different from different experiments, your y value can be different. This means that when x is equal to simple x, when capital X is the label for the variable, simple x is a value. So this means that when x is equal to simple x, y is a random variable with some probability distribution. For a fixed x, y can vary. So it can be considered as a random variable. And if it is a random variable, we can talk about some probability distribution. Usually we don't know what the probability distribution is, but if it is a random variable, there is a probability distribution. So let us assume actually a situation like this. Suppose you are considering a certain y variable, and if you observe the y value for a fixed x, then again and again and again, if you repeat this experiment with the same x, you might get different values of y. Say, for example, x is equal to whatever this value here. Let me use my pen a little bit. Right. Suppose, for example, mm, you are considering a particular x value, say some value x here. So for that x, you have several y values, possible y values. If you carry out the experiment at another value of x, it is possible for the y value to be in a certain range, right? Y can be any of these, right? like that. Suppose for different values of x, if you carry out, you are not really carrying out the experiment at very large number of x values. But here what you are considering is what will happen if we do this. Suppose the situation is going to be like this. So that means for a given x, y will be in a certain range. Maybe most of the y values are close to the somewhere in the center. The same y value will be very, very close values will be here, large number, small number of y values here, and again small number of y values will be here. Like if you consider, for example, here you can see that one or two observations here. Most of the observations are in the middle, and then few observation at this end. Right. Now, so that's what I'm saying, that for a given x, y can be different, and therefore for these y values, there is some distribution. For these y values, there is another distribution of y. There is for these, the distribution may be different, and so it is usually different. Right. Okay. So now, for each distribution, there is an expected value, that is the population mean. So this can be considered as the population of y values that we would get if we repeat the experiment at x equal to x value, right? So that there are large number of possible values for y when x is equal to say x1. So that can be considered as the population of y values. And if we consider another x value, so say x2, there are large number of possible values for y. So that can be considered as the population of y when x is equal to x2. Like that. So for this population, there is a population mean of y value. Suppose that mean is somewhere here. For this population of y values, there is a mean maybe somewhere here, right? For the other population, maybe at x equal to x3, mean maybe somewhere here. Population means, right? So we are going to assume that these means, so this is the mean of y value when x is equal to x1. This is the mean of y values when x is equal to x2. This is the mean of y values when x is equal to x3 and so on. So we are going to assume that expected value, that is the mean of y for a given x, is some function of x. It's a function of x, fx. Right. So here usually we assume that this function is a smooth function, right? So what we are actually assuming is that expected value of y given x is approximately fx, even though we usually take it to be equal, right? So practically expected value of y given x will be approximately some smooth function of fx. That is the assumption. So if that assumption is not reasonable, then a regression method will not work. The regression method will work if only you can assume that this expected value of y for different x's are behaving as a function of x in a smooth fashion. Right. So then for a given x y value here, another y value here, another y value here, and so on. So a y value can be written as the expected value plus something. For this y value, it is equal to this expected value plus this. For this y value here, it is equal to this expected value minus something. So therefore, for a given x, for example, here, expected value may be somewhere here for the population of y values. So for a y value here is expected value plus something, this distance. For a y value here, that is going to be expected value minus something. So therefore, generally, we can write down the model as y is equal to expected value of y given x plus some quantity usually denoted by epsilon. right? So if expected value of y given x is fx, then it can be written as fx plus epsilon. So this is called the regression model for y in terms of x, right? So this part is a mathematical equation. So that part is called the deterministic part of the model. And y will be a random variable. Therefore, epsilon will also be a random variable. Right? So for a given pair of observations, if you have xi, yi, in that case, that yi can be written as f evaluated at xi plus some epsilon I. Right? So that is uh, the model for individual observations. So this is the model for individual pair of observations. This is the model in general for the random variable. Y is equal to fx plus epsilon. Now, in a practical situation, what will happen? In a practical situation, we are not going to observe y value for each possible x value. We will be probably doing the practice or practical only for some suitable or selected values of x only, right? So we will be actually considering a particular set of values for x only, even though there are other values of possible x's, right? So any of these values are possible for x, but we do the experiment maybe when x equal to 2, when x equal to 4, 6, and so on, whatever according to our uh, requirements, we will select some x values and we will do some experiment at those values they are only, and therefore actually uh, what we will be looking at only, we will be considering at that case the population of y values at this x value, population of y values at this x value, and so on. But still, we think that those means of those populations are still as a function of fx, right? So what we want to find out is actually this function here, fx. What is this function fx, right? For that, in order to find out that, we will be considering several possible populations. Still, the function will be the same. But of course, now we are not going to observe all these possible values for a given x. For this x, we will be randomly getting only 2 or 3 observations, maybe one in one situation, right? So here, for example, I have here 4 observations coming from this population, right? So the population of values are here. So these rounded, red colored rounded ones are the sample, selected values that means we got from our experiment, for example. All others are the possible values if we repeat the experiment again and again and again, large number of times. But we have done only 4 times the experiment, and these are the values we got. So we think that this is a random sample from this population. And similarly, in this situation, I have about again 3 values. So those are the values that we got for y when we did the experiment x equal to, say, for example, 3. But we consider this as a random sample of y values coming from this population of y values that would be generated if we repeat the experiment at x equal to 3 again and again and again, large number of times. Right? So this is therefore the population at the observed population of y values at observed values of x, and this is the sample. What we have is considered as a sample. So this is a sample from this population. This is a sample from this population. It's a random sample. We are assuming that's a random sample. And this is a random sample from this population and so on. So now the question is, how do we find out at least approximation for this actual curve here using the sample, right? How do we guess this function, right? Or estimate this function fx using the few observations that we have here, right? So if you look at this situation, you might think there are several possibilities. One possibility may be to draw, because remember that you will never see all of this, any of these things. This is not observable, right? This is just an assumption, right? What we observe is only this part, right? So we think that we have to now think what will be the shape of the function in the population based on what we have observed. So based on these points here, one might think that, okay, in the population also, in the population, the relationship is a straight line. One might think so, because these points are close to a straight line. Therefore, one might think in the population, there may be this, whatever the f of function may be a straight line. So one might think like that. Or one might think that it is a function like this, a green curve, it's a quadratic function. Or one might think that it's like this uh, black dash curve, it's a cubic function, right? So a person might guess several possible models for the population regression line based on the sample, right? So we have only this x1, y1, x2, y2, x3, y3, and several pairs of observations. For some of these pairs, x value will be the same, but usually y values will be different. Or maybe for this one, we have only one observation. Maybe for this population, we have only one observation. For this, we have only one observation. That is also possible. In most of the engineering problems, I have seen that kind of situations. For a given population, we give for a given condition, experimental condition, you have only one observation. But that is not the most favorable situation. You have to have at least two or three to get some idea about the variation, possible variation of y values for a given x. That is a very important idea to have in regression. But of course, with the cost considerations and so on, sometimes you may be able to get only one observation for a given condition, given x value. That is what I have seen in many situations. Right. So using the n pair of observation, we estimate the parameters in fx. So in the previous slide, I showed you that when you think of a model, that model is going to be a function of, maybe in this case, we are considering only one x. So it can be a linear regression model or even a nonlinear regression model, depending on what shape you see or what type of curve can you assume to go through the observed values of observed pairs of observations. The parameters are estimated using the method of least squares method, or method of maximum likelihood. So these are some mathematical methods used to derive the fitted regression line, or get some values for those beta node, beta 1, beta 3 in the model that we assume. So standard inference theory. So once you have fitted a model, then there are model adequacy checking, checking whether those betas are equal to 0, right? As simultaneously with checking whether all the betas are equal to 0, right? That is a F test that I mentioned in the previous video. Or maybe individual t test to test whether individual parameters are equal to 0 or not, right? So those things are called statistical inference. Those can be done only if certain assumptions can be made reasonably, right? So one important assumption that we have to make in order to carry out those F tests and T tests is the assumption that for a given value of x, for a fixed value of x, the distribution of y is normal with mean equal to fx and some variance. So that is, for example, if you consider this three-dimensional picture here, suppose this is x, This is y values, this is x. So for a given x, we think that the possible values of y values are distributed according to as a normal distribution with mean equal to this value here, fx. If this is x here, this value will be fx because this function is f. And variance is some value sigma square. And for the other, so for another value of x, again, we assume that in that situation, the mean is y variable is normally distributed with mean equal to fx with that x. So for example, here if x1 is x is equal to x1, so mean is equal to fx1. If here it is x2, x value, then this mean will be fx2, right? So this f of x, the mean value will be changing with x. But we are going to assume that for all the distribution, the variance is the same. So that assumption is called homoscedasticity assumption, assuming that the variances of all the distributions are the same. On the other hand, we assume that the means are changing according to this fx function that we assume, right? So that is an important assumption. It's called model assumption. So before making statistical inferences based on the fitted model, we must make sure that the model assumptions are reasonably valid. So once you have fitted the model using the least squares method or the method of maximum likelihood, you have the fitted model. But now you want to test whether these fitted coefficients are actually the good estimates or whether they the corresponding parameters are actually zero or not, right? So to carry out inferences, you have to make sure that the model assumption that, right, in addition to that, there are other assumptions also, right? We are assuming that all the y values that we have are independent, right? Y1, Y2, Y3 are independent. And also that is also an assumption. So, which is usually true because we are carrying out experiment independently. Therefore, there is no reason in general for one y value to depend on another y value. But we have to make sure those assumptions are satisfied, right? Or that otherwise those assumptions are reasonable. So in order to check whether those assumptions are reasonable, usually we want, after we fit a model, for that model after fitting, we can get the residuals. Residuals are actual y values, the difference between yi and yi hat values. Yi hat values are the fitted values from the model, right? So these are called residuals, that is equal to yi minus yi hat. So we carry out something called residual analysis to check whether the assumptions are reasonable, right? So I'm not going to go into the details why the assumptions can be satisfied, checked with these residuals. I will just tell you what usually done, right? And thereby you also, if you are fitting a regression model, you also should do these things, right? Yeah. Otherwise, if I go to explain the reasons behind those things, it will take long time, right? So residual analysis is an important part if you are going to make any inference using the regression model, right? So the fitted values, yi hat values, the residuals corresponding to that observation xi, yi is defined as yi minus yi hat. So sometimes people denote it by ei or sometimes people denote by ri to denote residual. The correct word is residual actually. Some people call it the error, that's why they use ei. But error is not the correct word in this case. The residual is the correct word. Residuals represent the differences between the observed responses and the responses predicted by the fitted model. If the model is appropriate, the residuals should behave like random errors. So there is a difference between errors and residuals. Errors are these quantities in the model. Yi is equal to expected value of y given x plus the quantity. That is what we call the error. Actually, here the word error does not mean a mistake or something. It is just the word that have been used for this term. That is just the difference between the mean, population mean, and the observed y value. So that is the difference between the population mean of y values and a particular y value. That is what you call the error. Otherwise, it doesn't mean necessarily a mistake or something. No, it's just a difference, difference, but it is called the error. So that is what error is. But residual is yi minus yi hat, right? So yi minus yi hat is the residual. That means yi minus fxi hat. It is the residual. So residual and errors are two different things, but of course, we expect residuals to behave like errors. So we expect the residuals to have similar properties like errors. So that's why the assumptions that we have about errors are usually tested using the residuals, right? So I think that is enough explanation about that. So residuals are the things that we use to test the model assumptions. So residual analysis mainly used to check whether the relationship between the response variable and the explanatory variable has been adequately modeled. That means whether the model selected by us is a suitable model. That is one thing that we can check whether the selected model is a suitable model. Right? Fx, for fx, we select some mathematical equation. So whether that equation that we have selected is a suitable equation. And also using residual analysis, we can check whether error terms have constant variance. Right? Here we have assumed that uh, error terms have constant variance. Right? Right. So here, for example, uh, error is epsilon I, and we are considering that the error terms will have constant variance. Right? In other words, for a given x, y will have constant variance. The same thing. For a given x, y will have some variance. For another x also, y will have the same variance. That is what you call the homoscedasticity assumption. So that assumption also can be checked by checking whether the residuals have this constant variance, right? Whether the residuals have the same variance at different x values. And also error terms are approximately normally distributed, right? So we have an assumption that about the errors are normally distributed. So when y is normally distributed with fx and variance sigma square, error will be normally distributed with mean 0 and variance sigma square. Right. So whether the y's are normally distributed for a given x can be tested by looking at whether the residuals are normally distributed. Whether the error terms are independent. Right. Usually this independence assumption is satisfied by the nature of we collect the data. If we are collecting data from independent experiments, then naturally these error terms will be independent and therefore y values will be independent. But if, for example, the data are collected over a period of time and if there is some order of collection data, in that kind of situations, checking whether the error terms are independent or not is important. And there are also, by using the residual analysis, we can check whether there are unusual observations such as outliers or influential observations. If there are such observations, then we should go back and check about those observations, whether they are kind of recording errors and some other kind of mistakes. If they are that kind of observations, and if we can correct them, we should correct them. Otherwise, uh, uh, if you cannot find out any reason for that, or but still you think it's an unusual observation, and if there are only few such observations, you might be able to, you may as well delete those observations before fitting the data, right? Before fitting models again. right? Before fitting, not the data, before fitting the models, right? Because these models may be affected very much by this kind of outliers or influential observations. So common graphical methods used in regression analysis include residual plots, normal probability plots, and plots of residuals against fitted values of explanatory variables. I will show these things using some examples a little later, right? So residuals are used to estimate so that is one use of residual, to check the assumptions regarding the model, what we call the model assumptions. Right? So model assumptions are checked using the residual analysis. What are the other uses? Residuals are also used to estimate that sigma square term, variance of y values for a given x. Right? So we use the variance of the residuals as an estimate for the sigma square. That is another use of the residuals. The commonly used estimate for sigma square is actually the mean squared error that I mentioned previously also, mean squared error. The more correct word would be mean square residual actually, because EI hat, sorry, epsilon I hat, epsilon i's are the errors, epsilon I hat are the residuals. So what we are looking at here is the squared residuals, taking the sum and dividing by n minus 2 to get some kind of average, right? Instead of dividing by n, we are dividing by n minus 2 for some mathematical reason here. So that quantity is called the mean squared error. So mean squared error is used as an estimate for the sigma square quantity. Mean square residuals instead of mean square error is the more correct word actually, but most of the books still use mean square error. So in order to check whether, for example, the fitted model is a suitable model, as I mentioned earlier, we can use residual analysis. So for that, what we do is we plot the residuals versus our x variable. If you have only x variable, you plot the residual versus that x. If you have several x variables, you plot the residual versus each x separately. Right? Now, suppose, for example, you had the scatter plot like this, or maybe you didn't look at the scatter plot. You directly fit a straight line without even looking at the scatter plot. If you look at the scatter plot, if you had this kind of picture, you would not fit a straight line model. You would fit a quadratic model. But the quadratic model is still a linear regression model in that case, only that instead of x, you will be using x square. Right? But if you didn't look at the scatter plot, you will not see any of these things. Suppose you directly fitted a straight line model as beta naught plus beta 1x. Right? So now you don't know whether your selected model is suitable or not. Right? But when you look at the residual plot in that case, you will see this kind of pattern. Right? This is the residual, this is the x variable. So when you plot the residual, if you see a pattern, that means residual is still a function of x. Right? So therefore, you should be able to improve your model by adding some other functions of x into the model. Right? The linear term, x term is not enough. That is what it says. So in other words, the model that you have selected is not a suitable model, adequate model. It's not an adequate model. So that's how you find out whether the selected model or that model that you have considered is a suitable model or not. One thing, of course, you can get some idea about a suitable model if you look at the the scatter plot. But otherwise, you will be able to catch that using the residual plot. And if you plot the residual versus x, right, in this case, sometimes instead of the row residuals, it's better to plot something called the standardized residuals or studentized residuals. There are two types, standardized residuals and studentized residuals. Those are obtained by dividing the residuals by some quantities to make it some kind of do a standardization, right? And when you plot standardized or studentized residual on the y-axis and x values on the x-axis, if you see this kind of picture, for example, for 1 or 2 x values, the standardized residuals are quite large, right? What you expect is if there are no extreme values, almost all the residuals should be between -3 and +3, right? So if you draw a horizontal line at +3 and -3, you know the residuals are usually around 0. There are positive residuals and negative residuals. So what you expect in general, if your model is suitable and if there are no outliers, then almost all the residuals must be between +3 and -3. And in addition to that, you would expect about 95% of the residuals to be between -2 and +2. Right? But now here you can see that there's a residual with a large size is 6 standardized residual, right? So what I mentioned about this +3, -3, and +2, -2 will apply for standardized or studentized residuals, right? So that's why you are making it, because there is a criterion that you can apply to check whether the residuals are indicating outliers or not if you use standardized or studentized residuals, right? And also to check the assumption of constant variance, you can use the residuals like this, right? You would expect the variance of the residuals when you plot uh, the the residuals, or in this case, you can again, it's better to always use standardized residuals or studentized residuals versus the fitted value. In this case, you can, if you have only one x value, you can plot it versus x also, right? So if you plot, suppose you get this kind of picture, right? This is not what you expect. What you mean by this one is the residuals will be randomly scattered within a horizontal band without any particular pattern. That's what you expect. If the model is good, if you selected model is good, and if the model assumption about the constant variance is valid, right? Then you expect your residuals to be scattered around this horizontal line 0 without any particular pattern. That is what you expect. But if you see any of this kind of shape, that means they are uh, uh, in a certain band with a equal width, but of course they are not around uh, a straight horizontal line 0. There is a pattern, right? Maybe points are, or the residuals are scattered within this band, but in a pattern. So that is an indication that your model selection is not good. Model selection is not good, even though the constant variance assumption is reasonable. If you have this kind of pattern, if you see this kind of pattern when you plot the standardized residuals versus the fitted value of x, that indicates constant variance assumption is not valid, because you can see that the variability of the residuals are increasing here, is increasing. Therefore, the homoscedasticity assumption is not valid in this situation. And if you see this kind of situation where the variability of the residuals is constant for different x values, but of course there is a pattern, right? So that indicates the model that you have selected, mathematical model that you have selected is not suitable. A constant variance assumption is okay, right? So like that, by looking at the residuals, you can decide certain things about the model assumptions, validity of the model assumptions, right? So I have given some details here, but I don't have time to explain all these things. So therefore, I will just leave it here. Uh, I will give you the corresponding note also. Therefore, you can read the note and thereby compare with the video and read the note and understand. Right. So I will just leave it for the note then. So let's look at an example. Right. I have taken this data from a research paper. Right. I'm not, I'm just considering naming them as X and Y. So actually, if you look at this thing, one might think, okay, there appears to be a positive relationship between Y and X. You might even consider it as a linear straight line relationship in this case, straight line relationship. So therefore, you might consider a straight line model. And here I'm asking, is it appropriate to connect the points? If yes, Y, and if not, no Y. Actually, when you have this kind of scatter, it is not advisable to connect the points. The connecting points will give you some idea about that is the actual relationship between X and Y, which is not usually true, right? If you carry out another set of experiment, your points will be different. And in that case, the pattern you will see will be different. So therefore, this the pattern you will see by connecting the points is not the real relationship between X and Y, right? So therefore, I would expect, I would advise not to connect the points unless if it is really necessary, right? Of course, connecting the point may be useful if you want to just to show you that there is a upward trend, for example. But upward trend also can be seen from this without connecting. Right? But I'm not saying that it is illegal or something to do this kind of thing. But the thing is that may give you a false impression also. So therefore, it's better to avoid any possible false impression. Right. So because it looks like a straight line relationship, right? There is an evidence of a straight line relationship. We might assume that y is equal to fx plus some epsilon, where fx is a smooth function. It might be a straight line, or it might be even a curve or something. Right? So here I have drawn a straight line. That is one possible model to consider. Remember, when you are considering the model, we are considering the model based on the sample. Here, this scatter plot obtained from the sample. But actually, the model that we are considering is for the population, not for this particular sample. The red line represents the possible model for the apparent relationship in the population. So this relationship, right? However, would the apparent pattern change if the experiment were repeated? Yes. So apparent pattern here we get by connecting this thing will of course change if we repeat the experiment. The actual relationship would be clearer if we have several y values for each x, right? Rather than in this case for a given x, you have only one y value. But instead of one y value, if you have several y values here, several y values here, you might have a situation like that. So in that, if you that was the situation, you might be able to get a more accurate picture of the relationship that would be in the population, right? For example, in this case, uh, two possible models you may be considering at the beginning, right? A straight line model and also probably a curve might be a suitable model also, right? So therefore, if you have more observations, it will help you to think of several possible models. That's a good thing. And then you can fit all those models and then compare and come to a decision at the end, as I explained in the previous video, part 2. So the question is which model is better? Right? So for example, I have fitted here both models. I am using R here to fit the model. So I have the data in a data frame called, uh, in this case, I have the data in a CSV file, df.csv. df means data frame. So in that data frame, I have one column y values, another column x values. Right. So this is how you fit a linear model with x only. So here by this model one, I call it the model one. LM is the R function. Uh, by this command, I fit the model y is equal to beta naught plus beta 1 x straight line model using the data in this data frame. I have read the data frame using read.csv, that is R command. So this df is now in R. Now I use that data, df data, to get this model. And second model, I am considering a quadratic model. So again, I'm using this same function, y. Now here it has x plus uh, I square, I of s square, x square. So that means this is how you specify a polynomial type model in R, right? So this is actually fitting the model beta naught plus beta x plus, sorry, beta naught plus beta 1 x plus beta 2 x square, for example, for a quadratic term. So I fit the both models, and then using those available data. So then what I do is I want to actually draw these two fitted functions. So for that I'm using these commands. I'm not going to explain these commands here. So I have got, uh, well, I have those two curves here. These are the fitted curves actually. This is the fitted straight line curve, straight line. This is the fitted quadratic curve. So now I want to check which of this is better, right? So this is the output. One part of output I have obtained, that's called using ANOVA, analysis of variance for this regression, right? That actually carries out that F test that I mentioned earlier, testing whether all the coefficients for X variable in the first model and in the second one, X and X square, are zero or not. So here for the model one, I'm checking whether the coefficient for X is zero or not. The p-value is almost zero. Therefore, I decide that beta 1 is not equal to 0. That's what I can do in this case, checking using the F test. For the model, I have also got the summary of model 1. It gives me the fitted model coefficient. So here it says the beta naught estimated value for the beta naught is negative 12.222. Beta 1 term estimated value is 9 point something. And these are the results of the t-tests that I mentioned, individual t-tests. So we look at the p-values. This p-value is less than 0.05. Therefore, we decide that beta naught term is not equal to 0, right? And this p-value is much smaller than 0.05. Therefore, we decide that beta 1 term is also not 0 in the regression model if we consider the straight line model, right? Residual standard error, as I mentioned, this is the estimate of the sigma residual standard error. Multiple R squared. R squared value here is 0.807. Adjusted R square is also 0.8, right? Here we have only one X variable now. So R square and adjusted R square are almost the same. So this means this straight line model can explain about 80% of the variability in the y values, right? But the remaining 20% of the variability cannot be explained by this model. Right? So that's giving you some idea about how good this model is. Right? Now let us look at the model 2. Model 2, again, now it is testing whether this is the uh, the first F test. In this case, let me just write down something here. This is testing H naught. Now, the model that we considered is uh, y is equal to beta naught plus beta 1 x plus beta 2 x square. That is plus an error. That is the model that we have considered. So this is your fx part. Right? So here, using this F test here, we are testing H naught whether beta 1 is equal to beta 2 is equal to 0, whether both of them are equal to 0 versus H1 at least one of beta 1 and beta 2 not equal to 0. Right? So you can see that, oh, oh, okay, not that one. Actually, here it is showing ANOVA, ANOVA model here. It's not directly showing the output of this hypothesis. It's showing separate F tests also, right? So, uh, so this actually in this R, in Minitab and so on, it will be showing directly this output of F test. In R, it is showing something called partial F test, right? So if you fit X at the beginning, it will show that X is import. And when X is in the model, when you add the X square term, it is also significant, right? So that's what it shows. That in that way, it shows that when both variables are in the model, both variables are significant. So that means both of these are non-zero. That's how you have to interpret this output, right? In some other statistical packages, it will give you just one F value, and based on that, we can see whether this hypothesis is rejected or not. So in this case, we can reject this hypothesis because these both F values are actually what you have to look at is finally this one, because this will be the final F value, right? When both variables are in the model. So that is a significant value. That is less than 0.05. Therefore, we reject H naught. So therefore, if you want, now you can carry out individual t-tests. But in this case, it's not necessary because we have seen that both coefficients are significant from this output itself, right? So, I know whatever, but what are the other things? This one doesn't have model 2, this doesn't have R square value and so on. Yeah, so this gives you the sequential ANOVA table. Sequential ANOVA table. So if you have several variables, it gives you F values for sequential, right? So the first one, if you include this X at the beginning, this is the F value for that model. And then this is the F value for the model that has both variables. Right. So that's what you mean by sequential ANOVA. ANOVA table is for the quadratic model that we are considering here. The term X is significant when entered first into the model. So that's what this means. When X is entered into the model first, it is significant. The term X square is also significant after X has been included, since its p-value is this value. So that means after including X, um, X square term is still significant. Therefore, there is evidence of a curved relationship between X and Y. So actually it tells you that a straight line model is not enough, right? After you have included, you can still include X square term and still that term is also significant. So therefore, straight line model is not adequate, right? Hence, the quadratic model is more appropriate than a simple linear regression model. Right? And also, if you look at the R square value for model 2, you can see that the adjusted R square we should look at now, because we are comparing two models with different number of variables. In the First model, you had only one x variable. In the other one, you have x and x square both. So therefore, just comparing r square will not be the good thing to do, right? You should be comparing adjusted r square values. So for the model 2, adjusted r square is 0.859. For the previous model, adjusted R square was only zero point 0.8, right? So therefore, with respect to our adjusted R square value, second model is better. And the other thing is, even if it has two variables, still it is just a function of the same x. So if you have just an observation of x, you don't have to measure another variable. From the same, you can get x square and then include into the model and get a better model. So in that case, therefore, the second model can be considered as better than the first model. Right. Now, but there can be some problems, for example, especially when you have those powers of the same variable, like in a polynomial model, right? So second model is actually a polynomial model, right? It has x and x square both in the model. In that kind of situations, for example, x and x square can be quite strongly correlated. Yeah, correlation between x and x square can be very high. If that is the situation, it is possible some multicollinearity problems occur. Right, something is happening to my computer. It's changing. I don't know. Okay, so in that kind of situations, therefore, it is reasonable to check whether it is possible to have multicollinearity problems in the model. Right? Remember, in the previous video, I told you that if there are multicollinearity problems, then the fitted model is going to be very unstable. Unstable. That means the model can be changed by a large amount. Even the coefficients, estimated coefficient can have different signs. In one model, positive sign, positive coefficient, the other one, negative coefficient. Large differences can occur just by changing one or two observations. That is what you mean by unstable. So that kind of models are not good even if it is a high R square. So in order to check whether multicollinearity problems existing, we have to look at something called variance inflation factor, VIF. Right. So in R, in order to get the variance inflation factors, you have to use some library called CAR and then say VIF model. So first of all, you have to load this library. Otherwise, it's generally not loaded into R. So calling library car, first of all, you have to install that uh, package called car and then library car to call it and then say VIF model 2 to get the variance inflation factors corresponding to the variables in that model, right? So in this case, you can see that the variation inflation factors are 19 and that is actually considered as a very high variance inflation factor. Models. Remember, I told you in the previous one, greater than 5 is considered as moderately high, and greater than 10 is very, very seriously high. Seriously high multicollinearity, right? Problems. So VIF values are very large, indicating strong multicollinearity between x and x square. Therefore, the individual coefficient tests in regression summary should not be interpreted directly. You have to interpret them with the quotient, right? So therefore, those t tests and so on will not be showing the correct results, right? In particular, the non-significance of the linear term x may be due to its strong association with the quadratic term. Non-significance. Did we see a non-significant in the uh, these def test? I have forgotten to look at the individual t test here, right? So in the individual t-test here, actually what has shown is x term is non-significant, and but x square term is significant. Right. So in that kind of situation, when there is a multicollinearity problem, usually what we do is, instead of using x as it is, we use standardized x values in the model. Right? So you standardize x by taking away some value and dividing by some value. Usually this is done by subtracting the mean of x and dividing by the standard deviation of x. And then x square will be calculated using those standardized values. So therefore, for example, x will be converted into something z. Z is equal to x minus the mean of x divided by the standard deviation of x. And then instead of x square, you will be considering z square. Right. So that's what I have done here. Calculated the standardized x and fitted the third model for y as using x standardized value and x standardized value square. Right. Now you can see that partial left tests show that both variables are significant. What we are interested in is actually the last value here as the f test. Right. So that is a significant value less than 0.05. So in that case, we see that not all variables are not all coefficients are equal to 0. So that means we decide that at least one of the coefficients should be non-zero. So that's the conclusion coming from that. Look at the R square value. R square value has not changed here. R square value doesn't change when you transform x variables by a linear transformation like this. Right? Standardizing is a linear transformation. So in that case, R square doesn't change. But now if you look at the VIF values to see whether there is any multicollinearity problem in the model now, you can see that now VIF values are just 1. It's okay. It's less than 5. So now there is no multicollinearity problem in the model. Therefore, the fitted model with the standardized X can be considered as the final model. Right. So here, but of course, now all of these p values that we looked at, right, were interpreted assuming that model assumptions are reasonable, right? We didn't check whether the model assumptions are reasonable yet, right? Usually that is the way. Usually we interpret those values and then look at and come to a decision assuming that the assumptions are reasonable. But anyway, once you come to a final model, you must check whether those assumptions were really valid. Otherwise, none of the conclusions you made up to now will not be valid. So therefore, this is a good point to do the residual analysis. So what I need is I need the fitted values from the final model that we have selected. That is the model 3. I want to get the residuals, and I have obtained standardized residuals and obtained studentized residuals also. Those all can be obtained from this one. I put all those things to the previous DF, degree of, data frame. At the beginning, I had only Y values and X values. Now I add the fitted values and the residuals and the standardized, all these are new columns to the original data frame. Right? So after that, I look at some graphs. The first graph I look at is actually uh, the standardized residuals versus the fitted values. Right? Especially because now we have two x variables, x actually z and z square, right? In that kind of situations, we look at standardized residuals versus the fitted values, right? So what we expect is some graph where the residuals are in a horizontal band between -3 and +3. We expect all of them to be with any particular pattern, right? So you can see that when you plot the residuals, all the residuals are actually here between -2 and +2, around 0 here. There's no pattern here, right? The residual plot suggests that the regression model is reasonably adequate, right? If the model was not adequate, there would have been some pattern here, still remaining pattern here in the residuals. But now there's no pattern. That means it looks like that we have taken all the patterns into our model, that we have modeled all the existing patterns. Right? Most standardized residuals lie between -2 and +2. Therefore, uh, there is no evidence of outliers, serious outliers. However, two observations with standardized residuals slightly less than -2 may be considered. So there's two slightly less than -2, but that's not a big problem as mentioned. We expect about 95% of the residuals to be within my -2 and +2, and almost all to be between -3 and +3. But anyway, it's better to look at these two observations which have just marginally greater than less than -2 here, right? So it may be considered as outliers and should be examined carefully. There is no strong evidence of non-constant variance because the variability, there's no evidence of increasing or something like that in what we looked at earlier. So it's therefore reasonable to assume that homoscedasticity assumption is also reasonable, right? So some books suggest this kind of criterion. If the absolute value of R is greater than 2, maybe it's a suspicious observation. If R is greater than, absolute value of R is greater than 3, possible outlier. So this is only a suspicious observation. So if possible, better to go back and check what are those observations, and how whether there was an error or something in recording and so on. So observations with standardized or student residuals larger than 2 or 3 in absolute value should be examined carefully. So what I have done is I have selected those two observations which have those large residuals. Uh, so what I have looked at is which are the residuals which are greater than 2, right? So which outliers are greater than 2, and I have identified them as outliers. For the moment, I have called them outliers. And this here, there is a one observation 26 as a standardized residual, slightly less than -2. So it may be regarded as a suspicion, slightly less than means absolute value is greater than 2. So it may be regarded as a suspicion observation or mild possible outlier. However, it is not a serious outlier because its residual is not close to -3, just larger than 2 in absolute value. Also, since its x value is around the middle of the range, it does not appear to be a high leverage point. That means that there will be no much effect from that observation. Right. So therefore, observation 26 should be checked carefully, but it should not be removed automatically. It is only a mildly suspicious observation. If it is found to be an error, it should be corrected if possible. If the error cannot be corrected, the observation may be removed. Especially that kind of observation can be removed if you already have enough data. But if you have only very few observations, removing that also can have serious effects, right? So in that case, maybe it's okay to keep it, right? If it's a genuine observation, it should be retained in the analysis. So that only that observation was considered in that case. So now we are checking standardized residual versus standardized X values, right? So this is again a general practice. Now we have a standardized X in the model, Z, right? After checking plotting the residual versus standardized residuals or studentized residuals versus the fitted values, then usually we should plot the residuals or actually preferably the standardized or studentized residuals versus each x variable you have in the model. That is done to see whether there is any remaining pattern in terms of that variable. Right. So here I have plotted versus the standardized x, the standardized residual. There is no pattern here. So therefore, there is no indication that any more functions of standardized x should be included in the model. This residual plot is checking whether there is any remaining pattern in the residuals after allowing for the curvature, right? So we have already allowed for the curvature by including the x square term, standardized x square term. From the graph, the residuals are fairly scattered around the zero line. There's no clear U-shape or inverted U-shape patterns here. Therefore, the quadratic term seems to have accounted reasonably well for the curvature in the relationships that is apparent in the scatter plot. Right. And then, so that is about the fitted model, adequacy of the fitted models, whether we have selected a suitable model. And then we have to check the normality assumption of the errors. So that is done by checking the normality of residuals, right? So for this, there are several methods. One graphical method called normal QQ plot. In that one, we expect the plot to be around some straight line, right? But many people have wrongly interpreted this thing as saying this line is the regression line. No, that is not the regression line. What we have is here is the sample quantiles and theoretical quantiles of the residuals plotted versus the theoretical quantiles of a normal distribution. Right? So if the residuals are normally distributed, sample quantiles should be approximately close to the theoretical quantiles of a normal distribution. Right? So this line actually shows sample quantile equal to theoretical quantile line. So that is not the regression line. Right? So what we expect is if the residuals are normally distributed, the sample quantile should be approximately close to the theoretical quantiles, and therefore these points should be closely scattered around a straight line. But this is not the regression line. That is wrongly interpreted by many researchers I have seen. Right. So this graph itself shows that normality assumption is okay, but there are some other statistical tests to test whether the residuals are normally distributed. For example, there is a test called Shapiro-Wilk test. So I have carried out the Shapiro-Wilk test for normality of residuals. In that case, the null hypothesis is that residuals are normally distributed versus alternative is residuals are not normally distributed. So in this case, when we carry out that Shapiro-Wilk test, the p-value is 0.59. So this is much larger than 0.05. So therefore, we do not reject H0. That means we accept H0. That means we decide that residuals are normally distributed. So from the graphical method as well as a formal normality test, both of these methods, we decide that the residuals are normally distributed, and thereby we infer that errors are also normally distributed. Therefore, that assumption is satisfied. Okay. And then I have also looked at something called Cook's distance, right? So these are not done most of the times, but Cook's distance, I have shown here the Cook's distance, observation number, and Cook's distance. This is some quantity that is calculated to identify which observations are have relatively large Cook's distances exceeding the reference line. Uh, so these are actually an indication of some um, influential observations. Influential observations. But they are not that serious, right? So I'm going to omit that part just to limit the time that I have already spent for this thing. As I mentioned, if you want, you can read the note because this will be included in the note, right? So Cook's distance can be considered as a measure of the adequacy, right? Now we are looking at in this one a different example. So the previous example is over from here after looking at Cook's distance and then coming to decisions with that one. But remember, even though those Cook's distance leverage values are very rarely used tests, but of course, normality test of the residuals and other residual analysis are very, very important, especially the homoscedasticity assumption must be checked. Normality assumption must be checked. Right? Those are very important. Right? I have not seen those things even in most of the papers. Right? So, I think this is a good place again to take a break. I'll stop my video, this part 3 at this point, and the next one, I'm going to consider this example uh, with some more observations where this is again coming from a data set in a research paper. We are looking at something called CBR data, CPR observations under different treatments. Right? So we will look at that example in the next video.